I'm very honored, to welcome you to this inaugural event hosted by both OIST and the Asia Society on the future of energy and climate. Now, without further ado, I want to kick it off. This is a joint event, and both OIST, the Okinawa Institute for Science and Technology, and the Asia Society, we have a passion for science, we have a passion for technology, we have a passion for policy, and most important, we have a passion for getting things done. And this forum, we aim to connect thought leaders with doers, whether it's in policymaking or whether it's in business. And we hope that we can all connect and learn from each other to actually make the world a better place. Without further ado, let me pass the baton to Professor Peter Gruss, the president of OIST, who will give some introductory remarks and then introduce our keynote speaker, Professor Chu.
Good morning and hi to everybody. My special welcome goes to Stephen Chu, our keynote speaker of today. Hi, Stephen, wherever you are. It is undeniable that human activities have warmed the atmosphere, ocean and land, and that widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred, simply speaking, everywhere. Human activities, of course, primarily the burning of fossil fuels, have fundamentally increased the concentration of greenhouse gases in Earth's atmosphere, warming the planet. Global climate change has already had an observable effect on the environment. Glaciers have shrunk, ice on rivers and lakes is breaking up earlier, plant and animal ranges have shifted and trees are flowering sooner. Burning fossil fuels for energy use creates most of these emissions. Making deep cuts in emissions will require switching away from burning fossil fuels and towards using electricity generated from low carbon sources. This includes phasing out coal-fired power plants, vastly increasing use of wind and solar power, switching to electrical vehicles, switching to heat pumps in buildings, and taking measures to conserve energy. That's a lot of things to do. And there's hardly anyone who is more qualified as a speaker in our energy and climate change series than Stephen Chu. He's known best for his research at Bell Laboratories and Stanford University regarding the cooling and trapping of atoms with laser light, for which he won the Nobel Prize in Physics in 1997, along with two of his colleagues. Here are a few highlights of his illustrious career. After obtaining his doctorate, he remained at Berkeley as a postdoctoral researcher for 2 years before joining Bell Labs, where he did his pioneering work on atomic physics. When he left Bell Labs, he became a professor of physics at Stanford University, serving as a chair of the physics department. At Stanford, Stephen Chu initiated the BioX program, which focuses on interdisciplinary research in biology and medicine. In 2004, Stephen Chu was appointed as the director of the Lawrence Berkeley National Laboratory, a US Department of Energy national laboratory, and joined UC Berkeley's Department of Physics and Department of Molecular and Cell Biology. Under Chu's leadership, the Lawrence Berkeley National Laboratory has been a center of research into biofuels and solar energy. Stephen Chu is a vocal advocate for more research into renewable energy and nuclear power, arguing that a shift away from fossil fuels is essential to combating climate change. Stephen also served as the 12th United States Secretary of Energy under President Barack Obama. Then he returned to Stanford, where he now is a professor of physics and a professor of molecular and cellular physiology. Stephen, thank you for joining us this morning, and we are all looking forward to your keynote address.
Without further ado, I would like to start. And so here I go. Hopefully one can see this. Is that showing up? Yes? All right. Anyway, I want to talk about the issues, energy, climate challenges, but also what are possible solutions to these issues. So for that, let me just see if I can do this. Very, very briefly, what is happening with our climate, where we're heading, and what are the solutions? The average temperature of the globe has gone up, most notably since about 1940, 1950, 1960, perhaps 1.1, maybe even up to 1.2 degrees since 1800s. What we are seeing today are things that I never thought I would live to see, that these changes are increasing. We're seeing more heat waves, forest fires, droughts, water shortages, crop failures. And this is a map of the water stress areas in the world, which is considerable. And I'm terribly afraid that these increased stresses will become economic stresses, perhaps even collapsed economies. And when economies in countries collapse, they create millions or tens of millions of refugees. The other thing we should note is the last time the Earth has seen this much CO2 in an atmosphere was maybe 3 to 5 million years ago, when the temperature was about 2 to 3 degrees centigrade warmer, not 1.5 or 2, and the sea level was about 10 to 20 meters higher. Now, in order to slow this increase in CO2 and, in fact, reverse it, if you look at the pathways needed to stay below 1.5 or even 2 degrees, what you see very quickly is before the end of this century, we're essentially going to have to stop all greenhouse gas emissions and, in fact, go negative in greenhouse gas emissions. And that's greenhouse gas emissions from everything, not just power and electricity generation, transportation, but from everything we do, chemicals, agriculture, plastics, you name it. All right, so that is the challenge, and what are the science and technology solutions? Well, we've made some great progress. Wind has climbed dramatically, but still it's only 5% of worldwide electricity generation. The technology continues to improve. And we're seeing more and more wind turbines, giant wind turbines, now being built off the coast of Great Britain, which are expected to be turning about 60% of the time. We see tremendous advances in solar power. The cost of solar modules has actually declined more than 200-fold since 1997. And again, solar adoption is rapidly increasing, but still a very small fraction of the world energy output. Nevertheless, the prices are coming down. In some of the best places around the world, it's already less than 2 cents a kilowatt hour, and they will continue to decline below 1.5 cents a kilowatt hour. But here's the challenge. As we go to more and more renewable energy, at 5, 10, even 20 or 30% renewable energy, it's easy because most of the energy generating infrastructure exists. But as you go above 50% and more, then you need backup generating capacity, you need energy storage, you need a much enhanced transmission and distribution system. And all of those things are part of the real costs of renewable energy. So let's talk about one of the key ingredients, energy storage. This is my favorite picture of a battery. When the wind is blowing in this picture, you pump water under the ground to a water tower. And so once that water is in that tower, if you need the water, you open a valve. So you do the work when energy is available, and then it's stored, but not in the form of a chemical electrical battery, but in form of water being lifted up. This is idea of so-called pumped hydro storage is the dominant form of energy storage we have around the world. More than 95% of all energy storage is simply pumped hydropower. China leads the world in pumped storage and also in long-distance transmission and distribution systems. Here you see a map of China. In the black and the red are very high voltage AC and DC lines. And I've now suddenly got an echo, so if someone can adjust the audio so I don't hear myself, that would be great. Thank you. And so here we see these transmission and distribution lines bringing renewable energy, wind and solar, from the northeast and northwest, and hydropower from the southwest part of China. But there's something else they haven't yet done, which is a real opportunity. And that is, if you have excess wind and solar, is it possible then to take this excess energy, because electricity has the property, if you don't use it, you lose it, but actually to divert the electricity that is not being used and to pump water up the hills in this great hydroelectric system they have. And so here's an opportunity for that. Now, in order to achieve 80% renewable energy in the United States, which is particularly rich in solar and wind power, it's been estimated that we would need 3 days of energy storage. And what that precisely means is that the equivalent energy storage, as if you could run the entire country electrical system on batteries or any other form of energy storage for 3 days. That doesn't sound like much to get to 80% renewables, but what that really translates into is that we would need about 1,000 or several thousand times more battery storage than we currently have today. And if we want to keep the prices moderate, tolerable, the cost target is going to be about $10 to $20 per kilowatt hour, which is 1/10 of the current cost of battery storage. And so this is a real challenge. And the question is, can we actually achieve this? Now, clean electricity, as low as a cent, or maybe 1.5 cents, as I said before, it is going to become a reality in 10 years at the best sites when it's available. And with that, you can actually open up very exciting opportunities in electrochemistry, including hydrogen production. And because at 1.5 cents a kilowatt hour, the cost of the energy to make the hydrogen is only 1/2 the gate price, the current price that oil refineries and other users of hydrogen use today. So it means it's within striking distance. But there are some issues with hydrogen. We need a hydrogen distribution system. And most importantly, if you make hydrogen at the best renewable energy sites, wind and solar, you need to ship it. And pipelines are not always available. We don't have a hydrogen pipeline system. We would need a new system, which is technically possible, polymer-lined pipes, so that the hydrogen doesn't brittle the pipes. Those things are done, but we need that infrastructure. And then furthermore, we will need to be able to ship the hydrogen, and shipping it in, for example, in liquid form, either by liquefying in terms of ammonia, perhaps cryogenic hydrogen. These things, we don't know whether they're going to be economically competitive, but people are looking at that. Energy storage due to heat. This is to say you take excess power from electrical power from wind and solar, figure out how to turn into heat storage where there are no geological sites that allow for hydro storage. And perhaps this can become competitive with chemical batteries. Again, there are several companies that have been started, many people looking at that, but still not proven. Now, the good news is electric vehicles are really taking off. They're right now about 5 to 10% of all new car sales around the world. And within a decade or two, they're expected to climb dramatically. An optimistic scenario would be by 2040, for example, majority of light-duty vehicles, or personal automobiles, delivery trucks, things of that nature, could be battery powered. But that's the good news. The bad news is at that time, that means that 45% of the new light-duty vehicles will still be internal combustion engines. And once you build that, they will probably be used for 15 to perhaps as many as 20 years. So this means this transition is going to take several decades. And so that is an issue with anything that of this magnitude. Going on further, the technical possibility of improving batteries is really increasing dramatically. The reference battery is located in this diagram. Here I'm plotting energy per unit weight and energy per unit volume on the y-axis. And we show the Tesla battery that was used in the S1 Tesla. We're expecting perhaps in 5 years or so that the energy density of this original S1 Tesla battery will have doubled in energy by weight and increase maybe 30 or 40% energy per unit volume. And so this is very exciting news. But there's been questions raised. What about the materials for the batteries? Will that drive when the electric vehicles go from 10% to 50 or 80% of market share, will the cost of materials make these batteries prohibitively expensive? The good news is we don't think so. For example, my colleagues and I have published a paper recently which says it should be possible to extract lithium from very salty waters. This is salt water that is produced when you find oil and natural gas. It has very high lithium content, and even from seawater, which fractionally is maybe 1 lithium atom per 20,000 sodium atoms. And what Chong Lu, who's now an assistant professor at the University of Chicago, has shown is that by running half a battery, by putting on a voltage in a pulsed field configuration, she was able to bring out the lithium out of seawater into iron phosphate, a very common battery material that's widely used. And then you flush out the salt water, put in fresh water, and reverse the voltage, and out comes lithium. And starting with 20,000 to 1 lithium to sodium ratio, you can get to 1-to-1 lithium to sodium. And with water that you produce when you drill for oil, you can get over 95% lithium out of this. The issue is, can you cycle this many times, 1,000 times, with the iron phosphate? And there is some degradation of the iron phosphate, and so there are ways in which one can overcome this. But if this or some other similar idea like this comes to pass, then we will have essentially 5,000 to 10,000 times more lithium, and for the next thousands of years, lithium will not be an issue. There is as much lithium in terms of the atomic number in the crust of the Earth as there is nitrogen. So lithium is actually not that uncommon. And so if we are able to produce lithium from salty water that you drill out of the ground or from the seawater, this would not be an issue. Well, what about the cathode material? Unfortunately, there is not enough cobalt, and in fact, I believe not even enough nickel in order to go to 80, 90, 100% light-duty vehicles of EVs. So I'm spending my time looking at lithium metal sulfur and lithium metal iron phosphate batteries. The lithium metal means you increase the energy density considerably, about tenfold from the current anodes of batteries. And we've recently done some research, soon to be submitted, where we have a sulfur battery. Now, unfortunately, the chemistry of lithium and sulfur is a bit tricky, but until the electrolyte, and the electrolyte combines with the sulfur, but until the electrolyte disappears, the battery seems to be very, very stable. And with half battery, we can do 1,000 cycles. We've also begun to look at iron phosphate lithium metal batteries with a new type of separator. And so far, there's no sign of degradation, but it's going to take about a half a year to get 1,000 cycles, charging and discharging at 1C, which is about 3 times faster than current batteries. All this is very, very encouraging, because if this works, the materials we are using are very inexpensive and could be mass produced. So these are examples of how progress is being made in batteries. Now, the real challenge is, can you start with CO2 and water and perhaps use some energy adding processes, whether it be thermochemical, biochemical, photochemical, and begin to make hydrogen, CO, and eventually liquid hydrocarbons. And very recently, there's been a bit of a breakthrough by a company founded by Craig Ventnor and Ham Smith, formerly Synthetic Genomics, now called Virdos. They've partnered with ExxonMobil, and over the last half dozen years, they have been able to increase the lipid production from a form of algae 5 or 6 times while still maintaining the reproductive rate. And so for the first time, it looks as though algae, biofuels made from algae, and the target is long hydrocarbon fuels, so kerosene-like fuels for jet fuel, which is very difficult to make without a Fischer-Tropsch process. And if you can do this, then you can have aviation fuel, which is one of the hardest things to produce from being fractionated from crude oil. So this has real potential. And so for the first time, I've become more excited about perhaps biofuels. I was very gung-ho 15 years ago, and then it turned out harder than expected. But with new advances in biology, these things are coming to pass. Why do we want liquid hydrocarbon fuels? Because if you look at a supertanker and ask, what's the cost per gallon of gasoline does it cost to ship and store crude oil halfway around the world? And the answer is about 2 cents a gallon. So the transcontinental supertanker is one of the least expensive transcontinental energy shipping we know of. This is why if you make something like hydrogen or ammonia, you need to liquefy it and ship it. In any case, let me go on to something else we need and where there has been significant progress, and that is in this 4th agricultural revolution. And to that, we want to step back and look at where global greenhouse gas emissions come from. Most of the world was focused on electricity and heat production, which is about a quarter of all greenhouse gas emissions. But roughly the same fraction is due to agriculture, forestry, and land use. And so let's look at what sort of greenhouse gases are being produced from forestry, land use, and other things. One of those things, if you look at this, is N2O, and N2O is actually largely from agriculture, largely from over-fertilization, in fact, of agriculture. And there's actually more greenhouse gas emissions due to over-fertilization than there is due to the energy input of converting nitrogen into ammonia, into urea, into fertilizer. And so these are some of the things that have recently gotten a lot of attention. How do we stop greenhouse gas emissions from agriculture? One of the things that has gotten a lot of attention is that if we consume meat, and this is meat consumption per capita of the United States, Brazil, Canada, China, and others. And it turns out that among the meats we eat, beef is particularly troublesome. And it's because of the methane gas, the microbes within the beef, the rumen within their stomachs. These are organisms that produce methane. They take the food that the cattle have eaten. It's parasitic. They feed themselves to rob the cattle of the nutrients, produce methane, which is then burped out of the cattle. And here you see the greenhouse gas emissions, the life cycle assessment of beef cattle, swine, poultry, eggs, yogurt, cheese, and other things. And then and the difference, for example, between beef and pigs, more than a factor of 2, is the microbes. So what is being done about that? Well, there's several things being done. But before I talk about that, if you look at the world CO2 emissions around the world, China now leads the world. This is old data. This is, I think, 2005 or so. But right now, China is twice the United States. The United States is bigger than the EU 27 plus Great Britain. But if beef and dairy cattle were a country, the greenhouse gas emissions from just beef and dairy cattle would be more than the United States or Europe. So it is significant. Might also add that we have really modern agriculture has completely geoengineered the world. If you look at all the biomass due to humans and the animals we eat, that's about 96% of all the mammal mass in the world. Put on the other side, lions, tigers, bears, deer, mice, rats, and we're 96%. It's been found that if you feed cattle seaweed of a certain type, it can reduce greenhouse gas emissions significantly. And that is something really important. But the trouble is that from most sites around the world, they're not in feedlots. These are grazing animals. And so you don't have the opportunity to feed them the small amounts of seaweed, which actually reduces greenhouse gas emissions by 82%. How does it work? The seaweed actually suppresses the growth of the microbes in the cattle that produce the methane. But there's another approach, and that is vaccines. And now going under experimentation are vaccines. If you can vaccinate cattle so that you can greatly decrease these parasitic microbes in the guts of cattle, in the stomachs of them, you can really eliminate the methane and reduce the greenhouse gas emissions to that of pigs. And so there are experiments begun to see if this in fact is possible, because if it is possible and the beef tastes like beef, which it should, because we think that the microbes are only taking nutrients away from the cattle, they're not adding anything to the diet, that perhaps this would work. This is going further. There's a whole new world of what's called synthetic biology. And in synthetic biology, you begin to program into organisms, microbes, plants, and other organisms, entire metabolic pathways. And so you ask the bacteria, the microbes, or the plants to generate things that they normally would not have generated. And let me give you an example. In this effort to decrease the amount of greenhouse gas emissions from beef, there are a number of companies, Impossible Foods is one, which is trying to make hamburger-like material out of vegetables like soy. But in order to achieve the blood-like taste of this, there is a protein that's very similar to the hemoglobin found in cattle. And they have found that you can produce this hemoglobin-like molecules in yeast with genetically modified yeast to give it the beef flavor. And also other molecules like myosin found in the muscles of the meat we eat also can be generated synthetically in microbes. This is one example. Another example of synthetic biology is that you can produce microbes, and a company called Pivot Bio in the Bay Area in the United States, San Francisco Bay Area, has developed a cocktail of several microbes. When planted with corn, enter into a symbiotic relationship. So these microbes produce ammonia-like food that that is then fed by the microbes to the corn, and in return, the corn supplies these microbes with ingredients. So you enter in a symbiotic relationship, very much like soy roots with microbes. This is it's been working for half a dozen years, getting wider adoption. About half the fertilizer can be replaced. But remember, the big effort here is not only to reduce the energy content of the fertilizer, but to eliminate the nitrous oxides. Right now, half the fertilizer can be eliminated. They're moving towards much higher fraction. Perhaps all the fertilizer would be ideal, of course. They're producing microbes now for sorghum and wheat. And first, the nitrogen, you're going to replace the nitrogen-based fertilizers, but this company and others are now working on microbial phosphorus and potash production are the next targets. And so on the right-hand side in the photograph is corn with the microbes that produce the fertilizer the corn uses, and the left-hand side is more traditional corn. So this whole idea of synthetic biology and the programming, especially of microbes, has led to proliferation of companies that are trying to do this very powerful genetic manipulation with CRISPR-Cas9 methods, with machine learning, with robotics, and Pivot Bio is one example of dozens of companies doing this work. I'm on the board of Zymergen, and this is an example where they started with a strain of microbes used in large-scale production by one of the big agricultural companies, international agricultural companies, and by genetically programming using all the tricks of machine learning, robotics, and more powerful gene manipulation, Zymergen was able to produce a gene that was much more productive in a few years. Okay, so those are examples of exciting possibilities, but as we go into the future, we are going to exceed the goal of 1.5 degrees and even 2 degrees, I'm afraid, within a decade or two. And so it's become obvious that we will need to capture carbon dioxide from all point source emitters, whether it be electrical generations, steel, cement, chemicals, plastics, but we will need to generate means of capturing carbon directly from the atmosphere. And that could be done either by direct air capture, human-made methods of carbon capture, or it can be done with photosynthesis. And if you look at photosynthesis, and by photosynthesis, I'm not talking about the Amazonian rainforest or sub-Saharan forests. I'm talking about the crops we plant and the grasslands we plant. And it turns out that each year, the crops we plant for our own food capture about 30 billion tons of CO2 a year, and total human emissions in 2017 was roughly 40 gigatons of CO2, another 10 for the equivalent of methane and N2O. And so a large fraction of all the greenhouse gases we actually put up in the atmosphere each year due to human activity is in fact captured by the plants that we plant for food. And so this raises the possibility that if you take the corn, the wheat, the rice we grow, there's all the corn stover, the wheat straw, the rice straw, most of the plant is biomass, which means captured carbon from the air using solar power photosynthesis, if you can sequester that carbon under the ground inexpensively, this becomes a huge machine that captures carbon dioxide in the scale of tens of gigatons per year. In addition to that, you can think of all the land that we now lay fallow that we don't produce because of food overproduction in many countries, including the United States, where roughly a third of our acreage isn't planted. And if you plant crops that grow much faster than corn, miscanthus and switch has 5 times more biomass per acre than corn, you're then beginning to capture several gigatons. Back of the envelope suggests 3 gigatons of carbon dioxide each year from just fallow land. And this is really significant if you can find inexpensive ways of essentially burying it and not allowing the microbes to turn it into CO2 and methane. And so I'm giving this talk at a Breakthrough Energy Ventures retreat where they are looking very actively at schemes in order to do this, that it may be possible that this could be the cheapest way, perhaps as low as $50 per ton, of capturing CO2 from the atmosphere using plants. There are also other means of capturing CO2. There's well-known geological silicate cycles where carbon dioxide is converted from rocks, silicate rocks, into calcium carbonate type rocks, limestone type rocks. And the trouble with that is this is a geological process that takes thousands to millions of years. But people are beginning to look at ways of greatly accelerating that. Indeed, Yi Sui, myself, and Arun Majumdar at Stanford, Yi and I have discovered a way of turning calcium silicates into carbonates very, very quickly at low temperatures using aqueous solutions that was surprising. And the biggest input of this conversion is actually the grinding up of the rock into small pieces so you have a lot of surface area. But once you convert the silicates to carbonates, this is a very permanently sequestered carbon dioxide because it's beginning to look like limestone. And then you can try to pile this up in the way you would actually pile up as in landfill. This is just rock, limestone rock. There's also a very exciting possibility of adapting this process to make novel cements. And already there are companies beginning to emerge on using part of the cement process instead of Portland cement, looking for substitutes that now have a different curing process, again, to sequester carbon dioxide. And cement production today is about 8 to maybe even 10%, but 8% of CO2 emission is from cement production. So there's a possibility, just like in agriculture, you can flip it completely around, and what used to be a huge greenhouse gas emitter can be carbon absorber. And so, again, very exciting. I just mentioned a slide that will be discussed, I think, in the discussion section afterwards, of another process of developing concrete and using water curing in order to capture carbon dioxide. Okay, so I'm going to finish by saying that when all is said and done, we think of very ingenious ways, new science, synthetic biology, other things, in order to reduce the environmental impact, to slow the resources. But in the end, we also need to think about the growing population. We're 7.9 billion people. Whether we go to 11 billion or 10.5 billion people, it turns out that virtually every economic minister around the world says that we always want to have a growing population, and so that you have more young people being productive to support a smaller aging population. So in the United States, we call this a pyramid scheme or a Ponzi scheme. And so in order to become efficient and to reach a steady state, the solution so far has been to just continue making more babies and having population growth, but clearly this is not sustainable. And so we need to devise methods, and I believe there will be methods. Robotics is an intimate part of that, where you can have a shrinking population, but still growing prosperity with a shrinking population. And the final thing is we need a different measurement of wealth. Right now, wealth is measured by GDP per capita, and GDP is really the increased production and consumption of stuff, of automobiles, homes, energy, you name it. Now, the Human Development Index is a step in the right direction. It only puts a logarithmic weighting on GDP per capita in a country, but it also includes longevity and level of education as a measure of wealth. But in fact, as countries get wealthier, as when you begin to have warm homes in the winter, cool homes in the summer, and nutritious food, you're also now thinking of longevity, your quality of life in old age, security, physical security, continuing education, and living comfort. And so these are the things that really ultimately are measures of wealth, not just the making of more consumed stuff. And so with that, I will stop and we can enter into a discussion.
Professor Chu, thank you so much for your very candid remarks, for a fantastic, grand tour, of some of the new discoveries that you and some of your fellow scientists are pioneering. I think you've given us, some hope of some potential for a fourth agricultural revolution, synthetic biology, carbon capture. So absolutely fascinating. And I'm sure we will return to some of these issues in more detail in the Q&A. But now let me pass the baton to Terazawa-san. And Terazawa-san is an old friend and is currently the chairman and CEO of the Institute for Energy Economics Japan. And Terazawa-san is in a fantastic position, to sort of put Japan into context and give us a Japan perspective. I should mention that Terazawa-san, before assuming his current position, was the vice minister at METI, as well as a very close advisor to various prime ministers. So Terazawa-san, without further ado, please, the floor is yours.
Well, thank you very much for the kind introduction. Can you put the slides on the screen? I would like to explain the challenge towards carbon neutrality, especially from Japan's perspective. The first pillar of our policy should be the use of renewable energies, but there are very differences in the potential for renewable energies. Looking at solar power, the deserts in the Middle East, Australia, or the western coast of the Americas, they are rich in solar power. But relatively speaking, Japan and East Asia only have modest potential for solar power. For wind power, as you can see, the Western European countries are endowed with rich wind power. Unfortunately, most parts of East Asia are not endowed with strong wind power. Just giving one example, Chile is also rich in wind power, and their capacity utilization of wind turbines on average is about 64%. But in Japan, for regular wind power generation on land, onshore, is about 20%. So that makes a big difference in the cost between Japan and Chile. Having said so, excuse me. Oh yeah, that's fine. Japan has been trying especially to use solar power. And as you can see from this graph, the installed solar power PV capacity per flat land, Japan is much more installed in terms of density compared with other countries. So frankly, we have done a lot, but this is posing a challenge that the further installment of PV would have to receive the acceptance from the local community. So we should be promoting more PVs in Japan, but increasingly we are facing the need to coordinate and get the understanding from the local community. So this is why we need to have technology in place. Oh, excuse me. And this is a new technology. It's hard to pronounce. Perovskite solar cell. This solar cell is very different from the current solar cell, which is flat, heavy, and very energy and material intensive to manufacture. But this perovskite solar cell can be printed. It's lighter and it's flexible, and it doesn't use so much energy and materials in producing this perovskite solar cell. So theoretically, with this perovskite solar cells, you can install the new type of solar cells to places where it will not be very easy to install with the current solar panels. So we will expand the opportunities to install solar panels. So technology is important in this regard. Excuse me, I'm doing it wrong again. So with further use of renewable energies, we can increase the decarbonization of the power sector significantly. And this is our estimate for the global decarbonization of the power sector. As you can see, for advanced economies, we expect the decarbonization of the power sector to reach 85%, and for the emerging markets, 78%. So pretty high decarbonization we can expect in the power generation sector because of the use of renewable energies. But as I said, to capitalize on the decarbonization of the power sector, it is important to increase the level of the use of electricity. Electrification is very important because it is easier to decarbonize. But we have done a global estimation, and as of 2050, depending on the assumptions, the ratio of electricity would go up, but our expectation is that it will fall short of the 40%. So the remaining 60% will be in the hard to electrify sectors. So as I said, the power sector can be more easily decarbonized. So it is important to increase the electricity ratio. And to make that happen, one area is EVs, electrical vehicles. One of the problems for EVs is that the driving distance is limited because of the battery capacity. And here we have the old solid-state battery cars. And this example is from Toyota. And based on the current projection with this all solid-state battery car, the driving distance can be extended by 70%. And it's much safer than the current batteries. So this would help increase the electricity ratio further, not just in Japan, but globally. But the problem is that while we'll do our best to increase the electricity ratio, probably it will have its limits around 50%, maybe 55%. So the remaining 50% of the energy demand will be in the hard to electrify sectors, like in the industry or the transportation. And as you can see from the right side graph, it is much easier to reduce CO2 emissions for the power sector, but much more difficult to reduce CO2 emission in the non-power sector. So people talk about renewable energy, that's fine, but people tend to focus on the power sector. But we have to look at the non-power sector, which is about half. How to decarbonize the non-power sector. That is an extremely difficult challenge. And Dr. Chu has already used my slide. The concrete sector or the cement sector is the CO2 emitting sector. It's well known. And this is being developed by Chugoku Electricity Power Company together with Kajima. And rather than emitting CO2 with this new technology, they expect the new type of cement to absorb CO2. So this is one very interesting example. Then another sector which has been known to be emitting CO2 is the steel producing sector. It is a huge problem. but we can find ways to reduce the CO2 emission by using hydrogen. And for the next 10 years or so, the plan is to co-inject hydrogen together with coal and coke to reduce the CO2 emission. And in the long future, in addition to have co-injection, in the long future, 100% use of hydrogen instead of coke is the goal for R&D, but it takes time. I mentioned hydrogen. Hydrogen will be very important in our efforts to decarbonize the non-power sector. I mentioned the steel sector, but also many industrial processes require high temperature heat. And usually that can go on and go off quickly. With electricity, it's not easy to achieve that. So how to generate high temperature heat, which can come in and go off very easily, that's the challenge. And hydrogen can be one solution to respond to address that need. And also hydrogen can be used for fuel cell vehicles, FCVs. And hydrogen can be turned into synthesized fuel to be used for aviation, for example. So hydrogen is very important to decarbonize half of the energy demand sector, which is hard to electrify. Actually, this is the area in which Japanese companies have a great potential to contribute. I mentioned hydrogen. The beauty of hydrogen is that when you burn hydrogen, you only get water, no CO2. But the difficulty of hydrogen is that if you have pipelines, as Dr. Chu said, you can ship those hydrogen, but turn it to liquid, you need to cool it down to below minus 253 degrees Celsius. For your reference, LNG, it is cooled down to minus 161 degrees Celsius. So LNG has been a challenge, but to liquefy hydrogen would be an extremely more difficult challenge. It's possible, but very expensive. So that leads to the right side, ammonia, NH3. It does not generate a CO2 when you burn it. But to make ammonia into liquid, you only need to cool it down to below minus 33 degrees Celsius. This is within the normal industrial activities, so it's much cheaper. So many of you might have heard or read in the newspapers the recent discussion about ammonia, and this is the reason why. Basically, ammonia is produced from hydrogen. It's a derivative of hydrogen, but it's much cheaper to transport. In fact, we've done an analysis to calculate the expected cost of transportation, well, the whole cost, including transportation, as of 2030. It appears the most expensive option is to liquefy hydrogen, but the cheapest option is to use ammonia as the carrier of hydrogen, and it will be even cheaper if you skip the process of reconverting ammonia back to hydrogen and use ammonia as fuel as it is. It's the cheapest option. But as I said, hydrogen, ammonia, they're produced from hydrogen, so we have to lower the cost for the production of hydrogen. There are a number of ways to produce hydrogen. One is to extract hydrogen from natural gas or fossil fuel. But in the process, CO2 will be emitted. So it's bad for the environment. And that's the reason why it is called gray hydrogen. The next option is that capture the CO2 that is produced in the process to produce hydrogen and put it into the underground. This is called CCS, carbon capture and storage. And this would basically decarbonize the hydrogen produced from fossil fuel. And this is called blue hydrogen. And the green hydrogen is probably easier to understand. Using the power generated from renewable energies and using the electrolysis to turn water into hydrogen. So there are three options, and people are talking about either blue or green. We've done a cost analysis of the expected cost of producing blue hydrogen and green hydrogen, and as of 2030, this is based on the assumption that the carbon price is put at $100 per ton of CO2, and even incorporating that the carbon prices of $100 per ton, As of 2030, the cost for blue hydrogen appears to be significantly cheaper than green hydrogen. The cost of electrolysis is very expensive. We expect for 2040 and 2050, the cost for green hydrogen should go down. But if we talk about the sequence of introduction, economics is very important. So we believe that the combination of blue hydrogen transported as ammonia is probably the first step in the use of hydrogen or hydrogen derivative products. This is the final slide. As I explained, in Japan, it is hard to produce hydrogen. There is very short, we don't have too much renewable energies, and we don't have fossil fuels. So we have to import hydrogen and ammonia from somewhere. So we would require a global supply chain to provide hydrogen and ammonia, which will be very important to decarbonize the non-power sector. We had a similar experience with LNG. The first LNG cargo arrived in Japan in 1969 from Alaska. At the time, methane gas from the gas fields, oil fields was just burned. At the time, the business people had the foresight of cooling that waste methane gas into liquid LNG and carry those LNG from Alaska or Middle East or Indonesia, Brunei to Japan. And it was much cleaner. And for those of you in my age, we remember that as children, the sky was so dark. And one of the reasons was that we were burning oil to produce power. By turning it to LNG, we made our air much cleaner. So that was the experience with LNG. It sounds similar. It's more challenging. We have to cool it lower. But we've done it. We've succeeded in doing that with LNG. Japan was the pioneer, followed by Korea and Taiwan. And now you see a huge LNG market. And now the Europeans, for other reasons, are now talking about LNG. But it took us 50 years to arrive at where we are with the LNG supply chain. With our race against time to reduce CO2 emission, we have to accelerate this process shorter. And if we can develop a global supply chain, and hopefully together with other countries with the same conditions like Korea and Taiwan, they're in a similar situation, we can realize the economy of scale to reduce the cost of hydrogen and ammonia. Technology is important, but cost is important. One way is to realize economy of scale, and that is through developing a global supply chain together with other countries. I understand this is Asia Society, together with OIST. This is an excellent example for possible cooperation among Asian countries. Thank you very much.
Excellent, Terazawa-san. Thank you so much for a wonderful overview of Japan's ambition, to meet the goals. May I turn as a first question, perhaps, Professor Chu? May I ask you for a quick comment on how you look at Japan's hydrogen ambitions and how you view this?
Well, I agree completely that there's very different conditions of Japan versus the United States, and they need a chemical fuel that they can actually bring on board, and it's going to be ammonia, methanol, something, some liquid that you can ship via a supertanker. And I agree with those are the options that one has. Until offshore deep water wind become viable.
Thank you very much. Peter Gruss, may I ask you for some comments on Professor Chu's or Terazawa-san's remarks?
Sure. Pleasure. First, Stephen, this is one of the best talks I've heard that outlines the cutting-edge research and combines it with the possible options that we have in the future. I think this was a fantastic talk, and I would only hope that you can give many more of those to all other countries. And from my point of view, there are two things I would want maybe to address, that both of you can address. Firstly, Given what you said, it would be interesting to know if you have a roadmap, let's say for the next decade, how could we achieve carbon reduction, including the technologies you've pointed out, Steve? Secondly, you have spoken about many different technologies and new thoughts, very creative thoughts, how to reduce CO2. You didn't mention nuclear fusion, so I wonder what your position is regarding nuclear fusion.
Okay. First, despite significant demonstrations that are getting near 0.5 in terms of tokamak fusion, I think ITER will be successful ultimately scientifically, but it's going to be a tens of $billion adventure for the first few plants, and whether they can ever be economically viable is still uncertain. As a scientific experiment, I have full faith that they've been able to, over the years, do wonderful things, and not only viability. And we know from fission that the capex and the delays, and even though fusion radioactivity is in totally different scale than fission radioactivity, it is still radioactivity. And so these are things that I just don't know. I am chairing the Helmholtz review of the energy program in Germany over a 7-year period. It's entering into the 3rd year. And there's a lot of investment in fusion of the Helmholtz Association, and we have closely monitor what's happening, but it's difficult. So the roadmap, it's surprising. There are some low-tech things. Surprisingly, taking biomass, pelletizing it, putting it in sterilized plastic bags is being discussed in BEV in all seriousness. If that's, and one does a back of the envelope calculation on that, and you realize it's very low tech, it's bulldozers. The amount of stuff you have to put away is comparable to current landfill to be actually sequestering several gigatons. And so there are things like that that may have been overlooked that can be done very, very quickly. These other things, accelerating as quickly as possible, EV conversion, things of that nature, but and conservation. That's, of course, things that really one can do. But it is frightening how much inertia there is in the system, and how much resistance there still is. But I think some of these things that I talked about can be done in a sooner rather than later. Now, a lot of the other things, the biomanipulation of plants, that's going to take longer. But electricity generation, better transmission distribution, those things are technology we do have in hand, and that can be done quickly. But there has to be a stronger will.
Can I respond? If you're talking about 10-year time horizon, frankly, there's not too much that can be done because the deployment of technology takes time, and the development of a new technology takes time as well. So if we are talking about 10 years or 80 years from now, 2030, we have to use basically existing technology, existing infrastructure to reduce CO2 emission. One area is to reduce CO2 emission from the existing coal-fired power plants. People are not aware of this, but the fleet of coal-fired power plants in Japan is fairly young. After the Fukushima nuclear accident, many nuclear power plants were shut down. To provide the power to offset the loss of nuclear, power companies rushed to introduce coal-fired power plants. And they're coming into power last year and this year, brand new. It's very different from the old coal-fired power plants in UK or Germany. And the early retirement after 1 year of operation is very expensive. And actually, it comprises a significant portion of our power supply. So we will lose the power supply, which is not feasible. So what can we do to reduce the CO2 emission from the existing coal-fired power plants? One is low-tech, but to use biomass, coal-fired biomass with coal, which is not very scientific, but it works. That's one way. And the other is, I talked about ammonia, to use it as fuel. To coal-fire ammonia with coal will certainly reduce the CO2 emission. And it is possible to reduce the CO2 emission from the coal-fired power plants to the level of the existing gas-fired power plants. The rough estimate is that the CO2 emission emitted from the gas power plants compared with the coal-fired power plants is like 40% less CO2 emission. So the simple calculation is that if you can have 40% or 50% co-firing of biomass or ammonia with coal, you can realize a similar level of CO2 emission vis-a-vis the gas-fired power plants. It's more costly. So we need to put into a system to provide the incentives to do that. But in order to reduce CO2, that is certainly possible. And the other option is that many of you may not like this option, but energy is about realism. Out of the 36 remaining nuclear power plants in Japan, units, 10 units are only in operation. 26 are not still in operation. It's not about building a new nuclear plant. They do exist. You may not like this idea, but logically speaking, using the remaining 26 nuclear power plants, which is not in operation yet, is the pragmatic approach to reduce CO2 and also reduce our dependence on oil and gas from Russia. And additionally, in addition to restarting those nuclear power plants, the lifespan of the nuclear power reactors is set at 40 years as a principle. It can be extended to 60 years. But this extension would require authorization from the authority. And this is still very slow. So, number one is restarting the remaining 26 nuclear reactors and extending the use from 40 years to 60 years. That would provide us the bridge so that the new technology will come into place, as Dr. Chu explained. They will come in 2030, 2040, and 2050. We have to make the bridge before other new technology would come in.
Excellent point. Terazawa-san, thank you, and Professor Chu, thank you. I'd like to open it up, to the audience. And I know, Robbie, you have a couple of burning questions. Robbie, the floor is yours.
Okay, thanks very much. My name is Robert Feldman. I'm a senior advisor at Morgan Stanley, but I'm also currently still a professor in the Management of Technology program at Tokyo University of Science. And I've been looking a lot at this process of diffusion of new technology. I have a couple questions, one little comment. Professor Chu mentioned biofuels for jets. There's a small firm in Japan called Euglena that has been developing exactly this. There are already some planes flying on their biofuel. So it might be interesting to just Google Euglena and see what they're doing in that. On to questions. First of all, a question of cost benefit. We talk about diffusing these new energy technologies as a very costly process. It will cost a lot of money. However, there are also huge benefits. So for example, Japan currently imports about, by now with oil prices where they are, 4.5% of GDP every year. So 4.5% of GDP of our money goes abroad to the energy producers. If we were to invest in domestic renewable technology, would this investment pay for itself? That's the first question. I suspect it would, but I need to get your opinions on that. That's the first one. Second one, Professor Chu mentioned offshore wind. My understanding is that there are a number of relatively new technologies for floating offshore wind that are extremely good, good power generation, but they're also capable of withstanding hurricanes, typhoons, etc. So where do you see the role of offshore wind in Japan? I know that the International Energy Agency estimated that Japan's offshore wind capacity, this is a 2018 paper, is 9 times the electricity that Japan currently uses. So could we see a huge improvement in offshore wind? Third, and here I would also like to get Terazawa-san's experience from his long years of dealing with governments and companies. How do we accelerate this process? You mentioned a race against time. At the moment, we're losing. So how do we accelerate this energy diffusion process? Particularly, how do we lower the resistance of those who have built their lives on the old technologies and get them to adopt the new technologies? So that's the third question. Let me leave it at that. Thank you.
Should I respond first? For the first question of cost benefit, some of the technologies, you're right, it pays off. Like for solar power panels, they're quite cheap. So by investing in solar power panels, we can do away with many imported gas and oil. So in terms of the national wealth, it is better to probably to import solar panels from other countries, even if those are imported. Compared with the fuel import, that's better. But for other technologies, many technologies are still very expensive. So it depends on the technology. So we have to have a roadmap or sequence. The first stage is to use the available technology, which is commercially competitive, followed by the next stage, and then the more innovative technologies. So that's the process we have to envision. The next question about the wind power, that's a very good question. Japan is surrounded by waters, so potentially there should be huge potential for wind power generation in Japan. But the problem is that in addition to the wind relatively modest in Japan, with the exception of typhoons, the waters in Japan are not shallow. They go right deep. It's very different from North Sea. Recently in December, Mitsubishi Corporation won 3 auctions for the wind power installment, but they are all fixed bottom, aiming at shallow water installment. The potential for bottom fixed type wind power is not that great in Japan. So people assume, oh, Mitsubishi came up with a very cheap bid for the offshore wind power. Considering the waters surrounding us, we can do much more. That is much more than the reality. We should do that, but there will be a limit. So we have to go to the next stage of floating type offshore wind power. But I've talked with the leading executives of the heavy industries companies in Japan. But it appears, according to their assessment, the condition for Japan for floating type wind power generation is much more challenging. The current is very strong. In Japanese, we call it kuroshio, very, very strong. You have to find some way, somehow, to basically ensure that the wind power turbines will stay as it is. Otherwise, it will float to Alaska. So this is a challenge when the sea is deep. The next is that the wind, especially for typhoon, is very challenging. And if you consider the typical type of large-scale wind power generation, it can be 200 meters tall. Putting that floating on the sea against typhoon and a strong current and the strong waves followed by typhoon is a very, very, very insurmountable technological challenge. So we should do this. But even the best heavy industry companies in Japan are sort of hesitating to go for it. What was the third question?
Methods of accelerating.
Oh, okay. I think what is important is that the companies are asking us, yes, they know the innovation is necessary, but it's very expensive. And without the assurance that the demand will be there, in spite of the relative expensiveness of those technology, without that assurance, nobody would invest. They would do R&D or demonstration, but they do not put their money in actual investment unless that is in place. So we have to put into place a sort of policy framework to ensure we'll do our best to lower the cost, but it will still be relatively expensive. That hypothetically in 2030, this certain technology should be available, and even if it may be relatively expensive, the policy would offset that relative expensiveness as a clear outlook, predictability, to ensure that the companies can invest. This leads us to the question of carbon pricing, which is a matter of discussion within the Japanese government. But this is my personal view. It is important not to misunderstand the sequence or timing. Carbon pricing will work to make the transition from technology A, which may be bad for the environment, to technology B, which is good for the environment, but may be more expensive. But that kind of shift can only happen when the technology B is available. So I believe we should not put into place a strong carbon pricing today when technology B is not available, but making sure that a similar policy mechanism will kick in, say, 2030, so that it will make the assurance to the companies that in spite of the difference in the cost, they can be assured of the goal to invest. That's a reason. And for many companies with conventional technology, they complain a lot, but they care about the future. So if they see the opportunity assured, they will go ahead. That's the way to proceed.
Yeah, thanks very much. I think your emphasis on the chicken and egg problem is very, very helpful, and give them some assurance. And I agree entirely that your money is spent better on R&D development than it would be on a carbon pricing, although we need both. Professor Chu, may I ask you for some reactions?
Yeah, I agree. I agree that offshore wind, deep water offshore wind is very, very expensive. Shallow water offshore wind is twofold more expensive, but there's a hope in shallow waters like North Sea, also off the coast of New Jersey, other places in the United States, that it will be 1.5 times, within a factor of 1.2, 1.5 of onshore wind in a decade. But deep water wind, the deep water cabling, all those things are much more challenging. When I was Secretary of Energy, we had demonstrations of jet fuel, but it's really the economics. At that time, 2009 to 2013, the prospect of having biofuels be within 3x of conventional fossil fuel was not in the cards. And so what has happened since 2010-12 is that it's now looks like it could be within a factor of 2 of conventional fossil fuel. And a factor of 2 then begins to make it seem that it's reachable. So it's really, energy is about money. And all of the things we've been talking about were, when it was 4 times as much money, it was deemed too expensive for society. Within a factor of 2, then it's within earshot. And since the climate is getting much worse, then it's begun to be palatable. So I agree with these things. We watch everything very, very closely, and look for technological improvements that bring the cost of these things. I also noticed, I just want to make a quick comment to some of the things in terms of EVs and will they replace all internal combustion engine cars. And there will be a few instances where you are driving very long distances each day and you need quick refueling. And that's the only time when I see internal combustion engine cars might be favored. However, there are now being tested batteries that can charge perhaps out of a 300 or 400 mile range, 200 miles in about 6 or 8 minutes of charging. That's not available today, but we're talking now about 500 kilowatt charging rates, and you can do this every day and not damage the battery. Batteries like that are being tested. These very fast charging batteries will mean that a lot of the range anxiety that some people have, even though they may only take 1 or 2 long trips per year, if you're willing to wait 5-8 minutes to charge 200 miles while you're discharging at a service station, then you've reached the critical milestone where your battery lasts longer than the human bladder, and then things are okay again. But for high throughput industrial transportation, airplanes, heavy trucks, and high use vehicles, there could be for a while at least, internal combustion engine cars.
May I add a few comments?
Really heavy trucks.
And as for the heavy trucks, batteries are probably not practical. So that's where fuel cell vehicles, the use for fuel cell vehicles is considered to be stronger for long range heavy duty trucks. That's one thing. The second thing is that for those who are worried about the recharging or long distance driving, there is a plug-in hybrid option, which is in between the hybrid and the full EVs. By having plug-in hybrids, the actual consumption of fossil fuel will be minimized, but you can you don't have to be worried about the recharging or the long distance with the plug-in hybrid automobile. So for those use, I think that's an option. And also, there's discussion about having synthesized fuel, basically carbon-free fuel. For those who are worried about that, might be able to use synthesized fuel. In that case, they will be using internal combustion engine with those synthesized fuels. So EVs is probably the most center in our response. But fuel cell vehicles for trucks and maybe for those who are worried about that long distance driving, plug-in hybrid or synthesized fuel can also complement the main approach of having EVs.
Thank you very much. Professor Chu, if I may exercise my right as the moderator for a question. It's obviously a very complex, multi-layered problem. And it affects everybody globally. And it will require greater communication, greater collaboration amongst scientists, amongst technologists, as well as policymakers. If I may, how worried are you now that the world seems to be closing down, that America does not offer visas for top scientists from around the world? Is that something that you're concerned about, and what can be done about it?
I'm very concerned about it. The lifeblood of science is talking to other scientists. That is a collective thing that breakthroughs by one scientist in one country can stimulate other scientists around the world to go further. And so we collectively build on each other's shoulders. The idea that scientists from certain countries are going to be isolated from the United States, I think I've been very vocal about this the last several years. It's going to hurt the United States far more than any targeted country. So I'm extremely worried about it. The other thing, as you indicated, is that the challenge of climate is such an overwhelming challenge that it's really all hands on deck, and that we've got to really help each other. If one considers the unifying action of a very significant threat to the livelihood of everyone on Earth, this is certainly a challenge that needs our full cooperation. And many of the things we need to do require true international cooperation. Even this, how you actually give credits and carbon credits and this and that, and the sharing of best practices. If we retreat and erect walls between countries, it could be have a very appalling impact on progress.
No, thank you very much, Professor Chu. Thank you very much, Terazawa-san and Peter. We've unfortunately run out of time. We could go on. I just want to remind everybody that we are here, to keep the world open. We are here, all of us, as leaders of our respective institutions, to accelerate the global exchange, across borders, across as diverse as possible. And I very much hope that you will join us again